Okay, so we have some ABBA playing right now. This is going to be extremely important for today's lecture. It'll be interesting to see if any of this actually makes sense. Of course, how many of you have listened to ABBA in the past? Okay, excellent. Oh, excellent. This is good. All right. They're not quite as good as the Steve Miller Band, but they are an extremely good. Okay. ABBA has an extremely important lesson for us in probability. Okay. So it's painful, but I will stop this. I know we don't get to see outside, but maybe just having some music playing in the background. All right. One of the big questions in probability is counting. And one of the most common issues is counting the wrong thing, interpreting things the wrong way. When we did the birthday problem, we talked a while about what is exactly being asked. What are the assumptions? There are a lot of implicit assumptions that are being done. One of the assumptions is that maybe all birthdays are equally likely. Another is maybe no one is allowed in this class who was born on February 29th. This is why I constantly do events for admission to just make sure. It's not a protected category. You can discriminate based on the day of the year someone was born. Okay? It would change the analysis if you had to deal. But you could actually say, well, what is the probability of having a collision of birthdays if I now assume a certain distribution of days of the year? What kind of distributions would affect? So if someone's looking for a colloquium topic, that'd be a nice way to push something you've seen in this class further. One of the big questions is how many times does something happen? That's different than how often, or what's the probability. So versus what's the probability? My 70s history is not as good as it can be, so I will take this so I don't misspell people. I'm going to imagine we have 4 people named Agnetha, Benny, Bjorn, and I think there's 2 dots like this, and Anifrid. Now, if I was choosing the names of people for an exercise, I would never do this. Why would I never choose names like this? Yes? There's 2 A's and 2 B's. Right? And it's even worse, the 2 women are both A's and the 2 men are both B's. So you can't even do, female A, male A. So in some sense, this is really bad notation. Right? But let's imagine I have this group of people. Right? And it should be clear which group of people we're talking about. Right? And I want to form a subset of 2. So form a subset of 2. And I want each person is equally likely to be chosen. All right. And so if I do that, here's my question. What is the probability I choose, let's say, Agnetha and Benny? Any thoughts? Yes?
Is the probability one person is chosen independent of the probability somebody else is chosen?
I have not said that. What do you want to say when you see this? What's your instinct? Yes?
Your instinct is 1/4.
Instinct is 1/4?
No, sorry.
What's your instinct? 1/6. And how should I write 6? 4 choose 2. We have to be careful. While ABBA was a wonderful group and they were harmonious together for many years, there were 2 marriages and eventually 2 divorces. And so you had 2 husband-wife pairs. I believe at one point they were offered $250 million, either total or each, to get back together and tour. And they decided, you know what, we have enough money and we are quite content not to see each other again. We'll pass. So when I say everybody is equally likely, one possibility is if I have, let's call it now maybe A, B, C, D. That'll be easier. You could have A, B. you could have AC, AD, BC, BD, and CD. And if you do it like that, each one of these is equally likely, so the probability a specific thing occurs is just 1/6. But maybe A and B hate each other, and you cannot choose them together. And C and D hate each other, and you cannot choose them together. And in that case, you would have AC, AD, BC, and BD. That you would lose out on those two possibilities. How often is person A chosen in this one? 1/2. And person A is chosen 1/2 here. In both situations, each person is equally likely to be chosen. But the probability of having two people chosen together is different in the two settings. In one setting, it's 1/6. In another, what's the probability? No, I'm not telling you which. I'm saying, what's the probability in this setting that I choose two people together? 1/4 or 0. So if you want, you can imagine that in this case, we still have AB and AD, AB and CD. We're just now assigned 0 probabilities to those events, and we assign a probability of 1/4, whereas before we assigned a probability of 1/6 to each. So it's very easy to make these small counting errors. Are there dependencies? You have to always be aware and alert for something like that. Okay. Any other questions on ABBA? My chance to use all my ABBA knowledge gone. Hide. Any other questions on probability related to ABBA? I do not think it is likely that they will get together and tour again, sadly. All right. So what I want to do now is I want to turn to one of my favorite problems. I call it the cookie problem. A lot of people call it the stars and bars problem. It's another nice way to see some good combinatorics. And it can give you some warning about what grad school is like. So when I was a postdoc at Brown, I think I might have told you, there was a free food email list run by the grad students, where they would email each other saying, there's going to be an event at 4 o'clock followed by this type of food. And the graduate students would try to decide, is this worth it? Pizza, yes, crackers, no. So imagine we have 10 identical cookies and 5 distinct hungry grad students. Grad students like food, okay? If you're an engineering grad student, distinct may not be a legitimate assumption because sometimes the professors can't really tell the difference between the peons in the lab for the... We will assume we're in a discipline like mathematics where you can be recognized by your advisor, okay? I will, however, assume that the cookies are all identical. All I care about is how many cookies someone gets, not which cookies someone gets. So, how many ways to divide the 10 cookies among the 5 people? Okay, this is a really nice combinatorial problem. I've used this to solve a lot of research problems over the years. Later in the semester, we will actually revisit this and see how this applies to research. Can someone give me an upper bound as to how many ways there could be to divide the cookies? Yes?
10 to the 5th.
Upper bound 10 to the 5th. Why 10 to the 5th?
10 cookies, 5. No, wait, that's not. Sorry, I did it backwards. 5 to 10.
5 to the 10th, okay. Why 5 to the 10th?
There's 10 cookies, and each one of them has 5 choices on glucose.
Good, so we can give, one of 5 labels to each cookie. Okay, so this is one way to give an upper bound. There's at most 5 to the 10th possibilities. We could enumerate all these possibilities. It's not pleasant, right? 5 is greater than 4, right? So this is going to be greater than 4 to the 10th, which is 2 to the 20th, which is 2 to the 10th squared. 2 to the 10th is about 10 cubed, so that would be about 10 to the 6th. So there's at least a million things to check. The real question is, how much bigger than that is 5 to the 10th? It may be practical to do with a computer to go through the 5 to the 10th and just see. But we'd like a better way to do this. Okay? Can anybody give me a way to solve this problem? I don't care if it is efficient. I'm not in operations research anymore. It can be very slow. Can somebody give me a way to solve this problem? How could we count? Yes?
Write down every possible combination.
Oh dear God, yes. And so I actually maintain a Math Riddles page. This is the first riddle I ever posted on it. And I occasionally have people who go through and write down every possible combination. And even more really, I occasionally have somebody who does that correctly. So we will give the people the boring names of A, B, C, D, and E. So it could be 10, 0, 0, 0, 0. Now, do I have to really bother going through now 0, 10? Or can I just put like some number here talking about how many ways there are to permute this? So how many times should I count that? 5. So that's not so bad. The next one is I could do 9, 1, 0, 0, 0. And now I have to look at all the ways to permute that. How many ways are there to permute that? Yes? 5 choose 2. Because I have to choose 2 numbers. Is it 5 choose 2? Yes. So 5 choose 2 is the number of ways of choosing 2 spots. Those are going to be the spots that get the 9 and the 1. Okay, yes? Or I would say 2 factorial. So it's going to be, this 5 here is 5 choose 1. This is going to be 5 choose 2 times 2 factorial. 5 times 2 is 10. 5 choose 2 is 10 times 2 is 20. It should matter whether or not you get 9 cookies or 1 cookie. Right? And so 5 choose 2 is the number of ways of choosing the 2 special positions that are not 0. Right? What's next after 9 and 1? 8 and 2. How many ways are there to do 8 and 2? Same, also 20. What's after 8 and 2? Not 7 and 3, yes. 8, 1, 1. There's so much great stuff in this problem.
Why not 7 and 3?
I want to order my stuff so I don't forget any cases. I'm going to order based on the maximal number of cookies somebody gets. And then if I have 2 cases where somebody has the same, where we have the same maximum number of cookies, then I will compare the next largest number of cookies that someone gets. And I'll march down like that. So you want to be very careful when you do something like this that you do not omit a case. I have email after email after email of people doing the brute force and missing cases. Now what's nice is I know what the answer is, so I can just write, you missed something, and leave it at that. Okay? How many ways are there to do 8, 1, 1, 0, 0? All right, so 5 choose 3 seems like that should be part of it. That's going to choose the 3 parts that are in play. All right? So it feels like 5 choose 3 has got to be the start. Yes?
You have to do times 3 because there are 3 spaces between 8.
Yes. So if it's 3 factorial, then these would all be distinct. So if they were all distinct, then it would be 3 factorial, and that's why we had the 2 factorial here. So it's 3 factorial, but what do I love doing? Yes. It takes so little to make me happy. Yeah. Well, wait, what do I want to do it over? No, over 2 factorial would be stupid. Yeah, that's absurd to do it over 2 factorial. What should I do it over? No, not over 2. I mean, that's even more ridiculous than 2 factorial. I'm sorry? Nope. 2 factorial is halfway there. Play some Bon Jovi. I'm sorry? 1 factorial, exactly. 3 factorial over 1 factorial, 2 factorial. All right? Much, much better. Okay? Why is this better? Well, now I can see that this stuff down here is adding up to what I have upstairs. So what we're going to do is we're going to do a break now. We're going to do an aside on circular orderings, on multinomial coefficients, and then we'll come back and resume this problem. Okay. So what we've been doing right now is we've been going through all the different cases here. And we could have just multiplied by 3. But the idea is to try to sniff out what's going on. We have 3 distinguished places. But of the 3 elements, 2 of them are the same, and 1 of them is different. So we don't really care if it's 811 or 811. I can't tell the difference between the 2 ones. So Mississippi is a very hard state to spell. Can anyone spell it? Okay.
Mississippi.
Now listen to the question.
Oh.
All right, so how do you spell Mississippi? Mississippi. I'm sorry? Yes, yes, exactly.
Yep.
Anybody want to give me a good state? Ohio, no. I mean, pains me to say no to Ohio.
Iowa?
Iowa is a good state. I often use Maine because I'm local. Iowa is good. How many ways can I arrange the letters of Iowa?
They could spell Iowa or?
Just to spell anything. Any word. Doesn't have to be a real English word. 4 factorial. There are 4 factorial ways to arrange the letters in Iowa. How many ways are there to arrange the letters in Mississippi? So the first question is, how many letters are there in Mississippi? 4, 8, 9, 10, 11?
11.
So it should start off like an 11 factorial. And it would be an 11 factorial if all the letters were distinct. So let's make them distinct. We're going to introduce a couple of new letters to the alphabet. Any Dr. Seuss fans here? Ever read On Beyond Z? So when the regular English alphabet of 26 letters is too constraining, you can add some additional letters. So he has a whole book where he adds a bunch of letters to the alphabet. I'm going to add letters to my alphabet, but I'm going to add them with very boring names. I'm going to label them I1, I2, I3, and I4, S1, S2, S3, S4, P1, and P2. I now have distinct letters. Okay? How many ways are there to rearrange the letters in Mississippi where now all the letters are distinct in this expanded MathStat 341 alphabet? 11 factorial. Now we're going to forget the labels. So we have some rearrangement of the words Mississippi. Maybe we have the word S1, S2, I3, I4, P2, M, P1, I2, I1. Do I need 2 more S's? Probably. S4, S3. Right. So here is my new word. All I need to do now is I just erase the letters, the subscripts. But I could have also written down S2, S1, I4, I2, P1, M, P2, I3, I1, S3. And if I erase the labels, that will also look the same. And there's a lot more of them. I'm not going to go through all of them. So all of these would erase to the same. This is very similar to when we were introducing the n choose k. When we talked about how many ways were there to choose k when order matters, and then we divided by k factorial to get rid of the ordering. Now we need to get rid of the ordering. What should we divide 11 factorial by? Yes?
Divide by the number of ways you can switch 2 letters so that it doesn't change the word.
Okay, and so what would that be?
Maybe 10.
No, it's going to be a lot more than 10. Yes?
4 factorial plus 4 factorial.
almost, you're so close. Times 1 factorial, right? Don't forget the 1 factorial. Right? It's not going to change the value you get, but it will make it a lot easier to see what's going on. So I have 4 S's in fixed spots. How many ways are there to assign 4 labels to those S's? 4 factorial. So I have, if I just keep all the other indices fixed, if I just look at the indices on the S, there's 24 ways to assign the labels S1, S2, S3, S4 to the 4 S's here. Similarly for the I's, there's 4 factorial ways to do that. Similarly for the P's, there's 2 factorial ways to do that. And for the little itty bitty M, there's only 1 way to put it. The advantage of doing it this way is, what does the denominator add up to? 4 plus 4 plus 2 plus 1 is the top. It adds up to 11. Let's go back to 4 factorial. How should I really write 4 factorial?
4 factorial over 1 factorial, 1 factorial, 1 factorial, 1 factorial.
Yes. It looks horrible looking at it on the blackboard. But that's really what's going on. This is the number of ways of ordering the letters in Iowa, where all the letters are distinct. And here, this is the number of ways of ordering the letters in Mississippi, now taking into account. Okay? So what we can do now is we can introduce some notation. So n choose k was the number of ways of choosing k objects from n when order counts. This is n factorial over k factorial n minus k factorial. How could you view that? So think of it now, if I look at x plus y to the n, I'm going to get words involving just x's and y's. This is going to be how many words there are with exactly kx's and exactly n minus ky's. When I expand this out, maybe I do x plus y cubed. I'll have x cubed plus x, bad choice, x yx plus yxx. And the next one would be xyy plus yxy plus xyy, and the last one would be yyyy. This is telling me how many ways can I arrange. If I do 3 choose 1, I have 3 letters. I have 2 of one letter and 1 of the other. Yes?
So we can write n as something like k1 plus k2?
So we could write n as k1 plus k2. And this is saying we have k1 of the first letter and k2 of the second. What we're doing here is we're saying if we have n letters, we have k of the first one and n minus k of the second. So we can generalize this to a multinomial coefficient. So we could have n k1, k2, kl will be n factorial over k1 factorial, k2 factorial, kl factorial, and k1 plus kl equals n, and we want these to be non-negative. So I have L different letters. I have k1 copies of my first letter, k2 copies of my second, all the way up to kl copies of my last. How many ways can I arrange them and have distinguishable words? It would be n factorial over k1 factorial, k2 factorial, all the way up to kl factorial, what we just did before. Yes? Okay. This is the Mississippi problem, right? And so in Mississippi, k1 would be 4, k2 would be 4, k3 would be 2, k4 would be 1. Okay? Any questions about multinomial coefficient? So when we get to probability densities and distributions, and we're getting very close to that, these are going to be nice generalizations. We got the binomial coefficients by expanding out x plus y to the n. How do you think we get the multinomial? So where do you guess the multinomial would come from? So if the binomial is coming from expanding x plus y to the n, yes?
Like x plus y plus z to the n, or
Yeah.
x1 plus x2 plus x.
Right. And so if we only have 2 or 3 things, we can do x plus y plus z. If we have 4, maybe w plus x plus y plus z. But when we get to an arbitrary number, we stop being able to just use the nice letters like this. How many of you remember Calc 3, multivariable calculus? I won't look at the people who took it with me, so I won't feel sad. When you do your dimensions, you have your x-axis, your y-axis, your z-axis. Well, sometimes you do it the I, j, k. But then if you go into higher dimensional space, we then start using subscripts, x1, x2, x3, all the way up to xn. Or e1, e2, e3, all the way up to en for the basis vectors in linear algebra. So over here, we can play the same game. So if I want to look at x plus y plus z to the n, when I expand this out, this should be a sum over k1, k2, k3, k1 plus k2 plus k3 equals n, and choose k1, k2, k3, and then just continuing, I would have x to the k1, y to the k2, z to the k3. And if you think about what goes on, I have n factors. And what, yes?
Should it be a double summation, not a triple? Because the third term is determined?
Well, I mean, it depends how you want to write it.
Sure.
So if you want, I can actually drop k3, because k3 has to be n minus k1 minus k2. And so it really is a two-dimensional sum. It's, the real question is, what's the easiest way to write it down in a way that highlights what's going on? And so right now I want to highlight that K1, K2, and K3 are freely varying, but you're absolutely correct that K3 is now forced by the other two. And if you think what's going on, if I expand this out, I have n terms. For each term I choose either an x, a y, or a z. And when I want to look at what I get at the end, I'm going to collect all the terms that have the same power of x, same power of y, same power of z. So, x, 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 y, z, y, x would be the same as x, y, x, z, y. Now, how many more x's do I need? 3 more x's. These two would be counted as the same. This comes from choosing an x in the first term, x in the second, x in the third, x in the fourth, y in the fifth, z in the sixth, y in the seventh, x in the eighth. Over here it would be slightly different. I want to just know how many ways can I do that? Well, that's the same. I can just write I've got 5 x's, 1, 2, 3, 4, 5 x's, 2 y's, and a z. I'm just playing the Mississippi game. How many ways can I order that? All right. I'm not going to go into too much detail on the rest of this, but one of my favorite proof techniques is grouping, is using parentheses. How many of you have ever seen the trinomial expansion before today? Okay. What have you seen? You haven't seen the trinomial, but you've seen the binomial. How can I make this look like a binomial expansion? Yes?
You do like x plus y plus z.
Yeah, I can do it as x plus y plus z or x plus y plus z. Either way is fine. We'll do it as x plus y plus z to the n. And then this would become the sum, k goes from 0 to n, of x plus y to the k, z to the n minus k. And now what do I do to x plus y? Oh, and I've got to put the coefficient and choose k. X plus y to the k, z to the n minus k. And now what do I do to x plus y to the k? Yes, I expand that. So I would now have a sum, k goes from 0 to n. I would have a sum, L goes from 0 to k, n choose k. And now I would have k choose L, x to the L, y to the k minus L, z to the n minus k. And now it's an exercise in algebra. So I would let L be k1. I would let k minus L be k2. And I would let n minus k be k3. And then it would look a lot like this. And now all I would have to do is prove that this quantity is the same as that multinomial coefficient. And it just follows by expansion. So if I then had 4 things, I could just do grouping and grouping and grouping. And so you can understand the multinomial coefficients in terms of the binomial coefficients. And there's a really nice combinatorial story behind all of this. Okay? So these are useful. You'll see them in some statistics classes. We might see them in some distributions. You can use them in probably a horrible, horrible way of analyzing this. All right, what's the next case to consider? 7-3. All right, 7-3 is not too bad, right? It's just going to be 5 choose 2 times 2 factorial. It starts getting really bad when you have maybe, after you go down a little bit, maybe 3, 3, 2, 2, 2. How many ways are there to arrange those? Actually, that probably doesn't add up to the right number. All right, let's do that. 3, 3, 2, 2. So how many ways would there be to arrange this? Yes?
5 choose 4 times.
So 5 choose 4 to choose which spots? And now what do we multiply by?
4 factorial over 2 factorial times 2 factorial times 1 factorial.
For this one, I would say that this is one of the few times where there's not a 1 factorial, because we're not looking at the 0 anymore. You were choosing 4 spots to be. But now, let's look at what's going on. This is 5 choose 4. 5 choose 4 is 5 factorial over 4 factorial. Ooh, that 4 factorial cancels. What does this whole thing simplify to? This whole thing simplifies to, I'll just move this over so I have a little bit more space, to 5, 2, 2, 1. It just simplifies to the multinomial coefficient. If you look at this, this is 5 factorial over 2 factorial, 3 factorial. The 2 factorials cancel, and when the dust settles, you will actually see that you get 5 factorial over 3 factorial, 1 factorial, 1 factorial. And all of these are multinomial coefficients. Okay, there's a much better way to solve this problem. Is everybody comfortable with this way? And this introduces us to multinomials. All right. What I want to do now is I want to erase the multinomials and not look at them again today and go to a better approach. All right. This is where my childhood and your childhood might diverge. How many of you watched Sesame Street when you were a kid? All right, okay, excellent. So we have a visitor today, now tax deductible. So what can you tell me about Cookie Monster?
Eats a lot of cookies.
Eats a lot of cookies, okay? We are dealing with the original classic Cookie Monster, not the politically correct Cookie Monster who sings about cookies being a sometimes food and eats vegetables. All right, this is the original. And I believe some of the old Sesame Street episodes are not rated G because Cookie Monster encourages unhealthy eating. I'm not sure if this is true, but based on what else has happened in our society, I would not be surprised. The rumor that is definitely false is that Oscar no longer lives in a trash can, he lives in a recycling bin. That is false, but that does seem plausible as well. We will take the original classic Cookie Monster who always wants to eat cookies. So we want to divide 10 identical cookies among 5 distinct people. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, I'm going to consider 14 cookies. Okay? Cookie Monster now comes and gobbles some number of cookies. Okay? He will gobble 4 cookies. The difficulty is getting Cookie Monster to stop after eating just 4 cookies. All right? So we will assume we have done that. How many cookies have been gobbled up to the first division mark, up to the first gobbled cookie? So how many cookies are there before the first eaten cookie? 2. How many cookies are there between the first and the second eaten cookie? Between the second and the third? Between the third and the fourth? And between the fourth and infinity? 3. What do those numbers add up to? 10. There is a 1-to-1 correspondence with the ways Cookie Monster can eat 4 cookies from 10 as there are ways to divide 10 cookies among 5 people. When Cookie Monster eats 4 cookies, he partitions the set into 5. Everything up to the first, everything from first to second, from second to third, from third to fourth, from fourth onward. How many ways can Cookie Monster gobble 4 cookies from 14? Yes? 14 choose 4. And I'm going to write 14 choose 4 very pedantically as 10 plus 5 minus 1 choose 5 minus 1. Yes?
Is this a proof by story?
This is a proof by story. Yes. Brought to you by the letters. This is a proof by story. Isn't it much better than the brute force? Okay. I have tried to convince Sesame Street to let me come on and do this. Still pending. So if anybody has contacts with... Wait, is Sesame Street now on HBO?
Yeah, but it's on HBO and then afterwards they broadcast on PBS.
Okay. So I was trying to figure out who I need to talk to. All right. This is far faster than going through all the cases. And this is looking at a higher level as to what's going on. The general thing is it's cookies plus people minus 1 choose people minus 1. That's the formula. All right. We've been trained to be kind people. Sesame Street teaches us good values, allegedly. Something should be troublesome about this. Something should bother you. Yes?
Well, Cookie Monster could be eating cookies that were meant for someone.
Cookie Monster deserves cookies too. Yes?
If you divide it like that, then the third person there doesn't have anything.
Right, and we don't know if this person went to Amherst. This could be a Williams student. It could be a math major, right? Or a stats major, right? Does that bother you that somebody got no cookies? Yes. So the question is, can we fix this and ask maybe not how many ways are there to divide 10 cookies among 5 people, but I want to divide 10 cookies among 5 people so that everybody gets at least 1 cookie. There's a beautiful way of doing this, and it allows me to introduce some number theory. So, yes?
Well, if everyone automatically gets 1 cookie, then you're really down to just dividing 5.
Excellent. So that's the fast way is to say that really it's equivalent to just dividing 5 cookies. And we could actually do it a little bit more generally. What we're solving is what's called a Diophantine equation. We're solving an equation involving integer variables. So x1 plus x2 plus x3 plus x4 plus x5 equals 10. xi greater than or equal to 0 is an integer. That's what we're solving. What we now want to do is we want to put a constraint. And so the simplest constraint is everybody has to get at least 1 cookie. So at least 1 cookie, we can write xi as yi plus 1. And that will get us a new equation involving y's. Or maybe person I gets ci cookies or more. Maybe some people are more important than others. And so we don't necessarily have to give everybody equal numbers of cookies. In that case, we could have xi equals yi plus ci, and then that would lead to y1 plus y5 is 10 minus c1 plus c2 plus c3 plus c4 plus c5. And we can solve it very easily. It's now like we have a smaller number. So the way you should look at this is we're dividing the excess cookies. We first give everybody the bare minimum so that all the constraints are satisfied, that everybody's going to be happy. And then we divide the remaining cookies, because it doesn't matter which cookies you get. One of the nice applications of this is if you look at lotteries. Basically, lotteries are taxes on people who do not know how to do mathematics. Usually the payoff is lower than what you're putting in. But it's fun, and a lot of times the money goes to schools and whatnot. So if I give you a standard lottery, maybe there's 36 numbers, and you pick 6 numbers. How many ways are there to do that?
Does order matter?
Order does not matter.
Your repeat numbers.
That does matter. So it's a lot easier to analyze if you can't repeat numbers. It's sampling with versus sampling without replacement. So I pull out a 24, and then I can't use 24 again. So if you can't repeat numbers, it's 36 times 35 times 34 times 33 times 32 times 31. If, however, you can put the numbers back, it becomes more involved. And trying to calculate what's the probability you win if it's sampling with replacement. Do you think your odds are higher or lower of winning if you sample with replacement? Lower, right? Because there's now more possible combinations that can win. How much lower? So it turns out you can solve this using the cookie problem. It's a great way of putting in partitions the right way to figure out. And this allows us to calculate probabilities of events. There are occasionally stories where people have calculated that the amount of money available in the lottery is actually greater than it would cost to buy all the tickets. And that you can guarantee yourself a certain positive payout. And there are stories of people doing this. Most of the time, however, that's not going to be the case. Okay. So let's go back to this. All right. So I want to go back and I want to do a nice modification of the cookie problem. So everybody agrees that if I ask you how many ways are there to divide 10 cookies among 5 people, it's not hard. We now know how to do this. What if I now say you divide at most 10 cookies? You don't have to use all the cookies. So the solution is actually very easy. It's the sum. C goes from 0 to 10 of the number of cookies plus people minus 1 choose people minus 1. Right? So imagine I have C cookies to divide. That's the number of ways. And then I just go through all possible values of C. Okay. Yes?
Or you could just say that there are 6 people.
Or you could say there's 6 people. Maybe we can find somebody who would be willing to eat the extra cookies out of the goodness of their heart. And imagine that there's now 6 people. So now you have x1 plus x5 plus x6 equals 10. You introduce this one extra variable. And so whatever cookies you don't give to people 1 through 5, you give to person 6. How many ways are there now? So how many ways are there to divide 10 cookies among 6 people? Choose 6. So it'll be 10
No, 15 choose 5, sorry.
plus, right, 6 minus 1, choose 6 minus 1. We've got a theorem here. We can replace 5 with P, and this will still be true. And we can replace n, the number 10, with some number big M for max. We've just proved a binomial identity. Question? Oh, wait a minute. This should be, 6 should be p plus 1. Sorry. Because we have to have one more person. We have to have one more person. So 6 was 5 plus 1. Yes?
And should it also be m on the other side, or should it? No, it's still c.
It's still c. C is my variable of summation. Right. If you want, we're more likely to use maybe like the letter n for the summation if you want. We've just proven a formula about binomial sums. And what's strange is this is one where it's the top that's changing, not the bottom. This is a proof by story. Yes? I'm sorry? Oh, please, plus 1 minus 1. Thank you. Yes. So this is the power of this approach, is if you can tell the right story, you can prove an incredible wealth of results. It's very hard to prove these binomial identities, but by telling the story, we actually know what this sum is. And this is a wonderful trick of having an extra slack variable that just takes whatever's left over. Okay, any questions on this? Everybody is happy with dividing cookies. If people want, I will bring cookies to the next class. All right, just send me an email and remind me, because I'm sure I have cookies in my office. All right, so the last ones I want to do is I just want to quickly do circular ordering and the at least at most. So imagine we have a table 1, 2, 3, n minus 1, and n. And we want to know how many ways can we put n people around a table. If the seats have labels, how many ways are there? So if the seats are labeled, how many ways are there to put n people where it matters which seats you have? N factorial. But now what if we only care about relative ordering, only care about relative ordering? How many ways are there now? Yes?
Is it n factorial over n?
Yes. So it's n factorial divided by n, which now reduces to n minus 1 factorial. And the reason is if we no longer care about the seat labels, if we just care about the relative ordering, who's on your left, who's on your right, without loss of generality, you might as well put your first person here. And then just start filling in everybody else. And then you have n minus 1 choices for who goes here, n minus 2 for who goes here, and so on and so on and so on. So this is just circular orderings. And then the last is the at least and exactly. We've mentioned this before. The probability you get k is the probability at least k minus the probability at least k plus 1. Right? If I want to know what's the probability I have exactly k occurrences of something, if I can easily calculate getting at least k, and I can easily calculate at least k plus 1, then if I subtract, I can get the probability of exactly. So this is a very useful technique to calculate probabilities. It all comes down to how the information is conveyed to you. This should remind you of Bayes' theorem, where depending on how the information was given, certain probabilities are easier to calculate than others. And the whole point is you want to do the calculation where things are easiest. All right, so this now finishes chapters 1 through 6. We've now finished enough to have an exam. I will send you an email as to when you get this wonderful opportunity to work on fun problems. Okay.